So let's start off going back to what we had at the beginning of our work with the Riemann sums, which is just this idea that mathematicians had a lot of trouble figuring out the actual area under a curve from, let's say, A to B in this example, but that they could get close to the area, approximate the area under the curve, by drawing a bunch of little rectangles and then multiplying the height times the width of each rectangle to get the area, and then adding up those areas. So in this example that we have right here, the area is going to approximately equal the height times the width of this purple rectangle plus the height times the width of the blue rectangle plus the height times the width of the green rectangle, or approximately 28. So the general idea that we have is to get the area from A to B. We should start at A, multiply the height and width of each rectangle, to get the area. Add the areas. Stop at B. Now, the problem facing us when we use this method is that the rectangles up here don't touch the curve exactly. There's this little gap up here and here and here, making our estimate right here an underestimate of the actual area under the curve. To get the exact area, we need there to be no gaps. The question is, how do we do this? So let's write down our goal. To get the exact area, we need to draw rectangles with no gap. How can we do this? Well, unfortunately for us, if we have a curve, so let's just try a couple things here. I know that if I draw a rectangle like that, there's going to be this gap here. Not good. So I'm going to try drawing a thinner rectangle. How about that? Well, it turns out that if I zoom in and I look really closely here, there's still a gap. And even if I try doing this as thin as I possibly can, if I look really closely right there, still a gap. So, if a rectangle has any width, there's still a gap. So this caused big problems for mathematicians until I came up with the idea of, well, let's make a rectangle that's so infinitely thin that there really is no gap. It's an infinitely thin width. Like so. This was great for solving the problem, but mathematicians really choked on the idea of an infinitely thin width. It actually took quite a long time for this idea to win acceptance. Now that it has, however, it makes life a lot easier for us as long as we know a couple things about it. An infinitely thin width is called a differential. And it is written dx if the width is in the x direction, or as dy if the width is in the y direction. So an infinitely thin rectangle like that versus like that. This width here is dx because it's going side to side if we were to draw it into an actual regular rectangle. And this one, this is dy because the width, if we were going to make an actual rectangle, this width is in the y direction. Another important thing to note is an infinitely thin rectangle has a height exactly equal to the value of the function at that point. If this is our function, when x equals a and we draw our infinitely thin rectangle, height is the value of the function at a. We're going to assume this is f of x. And then width is dx because the width is going in this x direction. So to find the area from A to B of that curve that we were just working with, we're still going to do exactly the same thing. We're going to take a bunch of infinitely thin rectangles and so on. And we're going to add up the height times the width of each rectangle. Remember, this width is this infinitely thin. This little width right here times whatever this height is for each one. We're going to add up each of those, starting at our starting number over here at A and ending at our stopping number over here at B. And the thing is, if we can write an expression for the height of each of these infinitely thin rectangles in terms of the same variable that we're using for width, then we can use integration to find the area. So let's write that out. So let's say the equation of this curve is that f of x equals the square root of x plus 2. Then we can say that the area is the integral from our starting number to our ending number. We know that our infinitely small width is in the x direction, so it's going to be dx. And then the height of each rectangle, whatever the value is for x, this height is f of x, or root x plus 2. This right here is called an integral expression. And in this case, it's for the area under f of x between a and b. So what we're going to be asked about in the problems for this set of notes is we're going to be asked to write an expression, an integral expression to find area. So let's just write down the steps that we're going to have. So to write an integral expression for area, first you're going to be drawing a sample infinitely thin rectangle. And marking the width as dy or dx. Then we're going to write an expression for the rectangle's height using the same variable that's in the width. And then we're going to find the starting and stopping values.